Welcome to this explainer. Today, we are tracing the fundamental mechanics of reality. We're starting way down at the microscopic subatomic level, and we're going to scale all the way up to the very tangible mathematics of stoichiometry. If you've ever been fascinated by how the totally invisible rules of the microscopic universe end up dictating the solid physical world you interact with every single day, well, you are in exactly the right place. Okay, let's dive into this. We're working from a really dense set of study notes today, covering atomic structure, bonding, and stoichiometry. And to the untrained eye, a page packed with this much text and terminology can definitely be a little overwhelming, but that's exactly what we're going to tackle. We are going to unlock the secrets hidden within this text and transform those dense chemistry facts into crystal clear, connected concepts. Here is our quick roadmap for today. First up, inside the atom. Second, how atoms bond together. Third, giant covalent structures, and finally, the mathematics of moles. Our narrative arc is literally going to zoom out, starting at the tiniest microscopic level and ending with some very tangible, practical math. Let's get right into Section 1. Inside the atom, the subatomic cast of characters. So our subatomic cast basically breaks down into three main players: protons, neutrons, and electrons. Right in the nucleus, that super dense center of the atom, we have our protons. These guys carry a relative mass of 1 and a positive charge of +1. Sharing that tight space in the nucleus are the neutrons. They also have a relative mass of 1, but just like their name suggests, they are completely neutral, charge of 0. But out in the energy levels, the ones orbiting that nucleus, that's where we find the electrons. They carry a -1 charge, but their relative mass is just 1 over 1840. I mean, that mass is so incredibly, bizarrely tiny that we consider it entirely negligible when calculating the total mass of an atom. Simply put, the nucleus brings the weight, but the electrons bring the chemical action. And that actually leads us to a really fascinating quirk in chemistry: isotopes. Isotopes are distinct atoms of the exact same element, which means they have identical proton numbers, but they have different numbers of neutrons. Now, because isotopes have the exact same valence electron configuration, they display identical chemical properties. An element's chemical personality is entirely dictated by its electrons. However, because those extra or missing neutrons change the atomic mass, isotopes actually exhibit slightly different physical properties. So things like density or diffusion rates, they shift slightly just because of that varying mass sitting in the nucleus. Moving on to Section 2. How atoms bond together. Finding stability through interaction. We are now zooming out from single atoms to see how they actually solve their main problem of needing stable outer shells. Atoms basically employ two incredibly different strategies for finding that stability. Let's look at ionic bonding first. This is extreme, it's rigid, and it's highly transactional. It occurs between metallic and non-metallic atoms through the complete, absolute transfer of valence electrons. This creates oppositely charged ions that get locked together by strong, multidirectional electrostatic forces in what's called a giant ionic lattice. Because they are locked so tight, they have very high melting points, they're brittle, and they literally only conduct electricity when they're molten or aqueous, because that is the absolute only time those charged ions are actually free to move. Now contrast that entirely with covalent bonding. This happens between nonmetal atoms, and there is absolutely no transfer happening here. It is all about sharing electron pairs to achieve those stable outer shells. This forms simple molecular structures. Now, while the bonds between the atoms themselves are strong, the forces between the molecules, the van der Waals forces, are remarkably weak. Because of that, they have low melting points, they require very little energy to overcome, and since they lack mobile electrons or ions completely, they never conduct electricity. All right, Section 3. Giant covalent structures. Escalating the stakes to epic proportions. Now, what's really interesting about this next concept is how we scale up from simple molecules to massive, giant covalent macromolecules. Let's compare a few famous macromolecules. Think about diamond and silicon 4 oxide. In these specific structures, every single atom is firmly linked by strong, localized covalent bonds. The result? A locked, rigid, totally unyielding structure that boasts exceptional melting points and extreme hardness. But then, look at graphite. Graphite is a totally unique macromolecule. Instead of a rigid 3D grid, it's arranged in these flat, hexagonal layers. The forces between these sheets are incredibly weak, which allows them to just freely and easily slide right over one another. That sliding action is exactly why graphite acts as such a brilliant lubricant. And unlike our simple covalent molecules from earlier, graphite actually contains delocalized electrons that are totally free to move along those layers, so it conducts electricity. It is an absolutely incredible structural exception. Okay, so we've seen atoms, isotopes, lattices, and macromolecules. But all of this raises a pretty critical pivot question. Whether it's a simple molecule or a giant structure, these particles are infinitely small. So when we step into a chemistry lab in the real world, how do we count what we literally cannot see? And that brings us to section 4, the mathematics of moles, bridging the micro and the macro. This is where stoichiometry comes in to save the day. I know when we first dive into the math of the mole and gas calculations, it can definitely cause a little anxiety. But I promise you, the logic laid out here is highly, highly structured. Once we understand the core rules, stoichiometry becomes an incredibly powerful tool. It all starts with this massive, staggering number, 6.02 times 10 to the power of 23. You can basically think of this as the chemist's dozen. Just like a dozen always means 12, 1 mole represents exactly this many particles. It does not matter if it's a mole of carbon atoms or a mole of water molecules. It is always 6.02 times 10 to the 23rd particles. And here is the real magic. The mass of 1 mole of any substance is simply its relative formula mass expressed in grams. It flawlessly translates the atomic mass from our very first concept directly into tangible grams that we can actually weigh on a scale. And the rules get even more elegant when we look at gases, 24 cubic decimeters. So the crucial point is this. At room temperature and pressure, what chemists call RTP, 1 mole of any gas occupies this exact fixed molar volume. It absolutely doesn't matter if it's a heavy gas or super light gas. 1 mole will always take up exactly 24 cubic decimeters or 24,000 cubic centimeters. This builds perfectly into an actionable checklist for stoichiometry calculations. When you're working out gas questions, it's a simple 2-step process. Step 1, you rely on the core formula. Concentration equals moles divided by volume in cubic decimeters. But step 2 is where most people trip up. You must always check if your gas volumes need to be converted from cubic centimeters into cubic decimeters. You do this by dividing your cubic centimeters by 1,000 before plugging them into your calculation. Honestly, forgetting that step is the easiest way to fail a calculation. But if you remember that simple conversion rule, the math will perfectly reflect the reality every single time. We started today with the completely negligible mass of a single orbiting electron, and we scaled all the way up to billions of trillions of particles, perfectly predictable by a few simple mathematical rules. So I want to leave you with this provocative thought. If a single mole, a handful of matter you could easily hold right in your palm, contains exactly 6.02 times 10 to the 23rd particles, what does this invisible math reveal about the sheer, unfathomable, massive scale of the universe you interact with every single day? The physical reality we touch is governed by numbers so vast, yet rules so perfectly elegant. Thank you so much for joining me on this explainer. I really hope you never look at a physical object the exact same way again. Keep exploring.